my channel. So today we are going to discuss Gauss law and its application, which you can expect for your board exam. Now why should we study this Gauss law? Because Gauss law is a general law which is applicable for all closed surfaces. For geometries of sufficient symmetries, Gauss law simplifies the calculation of electric field. Gauss theorem. It gives a relationship between total flux passing through a closed surface and the charge enclosed by the surface. Gauss theorem states that the electric flux passing through a closed surface is equal to 1 by epsilon 0 times the net charge enclosed by that surface. Or mathematically we can express Gauss theorem as flux is equal to Q divided by epsilon 0, where Q is the net charge enclosed within that surface. So according to Gauss theorem, the flux through a surface is 1 by epsilon 0 times the charge enclosed by that surface, where epsilon 0 is permittivity. Now we will prove Gauss theorem. So here I am considering a positive charge. For the sake of simplicity, we will prove Gauss theorem for this positive point charge. Let plus Q be the positive point charge and R is the radius of a spherical surface, where plus Q is the center of that surface, and that spherical surface is known as Gaussian surface. We will see later on what is meant by Gaussian surface. Here the area vector ds and the electric field both are in same direction. So I can say that the angle between ds and E theta is 0 degree because both ds and E are in same direction. Now here we will prove the Gauss theorem. Okay, according to flux, the equation of electric flux d phi is equal to E dot ds. Since theta is equal to 0, you can write d phi is equal to E ds. According to Coulomb's law, E is equal to 1 by 4 pi epsilon 0 Q divided by R square, where R is the distance between the point and the charge Q. Here we are going to find the electric field on the surface of the spherical surface. So E is equal to 1 by 4 pi epsilon 0 Q divided by R square. This E can be substituted in the equation of d phi. So d phi becomes 1 by 4 pi epsilon 0 Q divided by R square into ds. So here we got an equation for d phi. Now we will find phi, that is flux, by integrating both sides. So phi is equal to closed integral of d phi, which is equal to closed integral of 1 by 4 pi epsilon 0 Q divided by R square ds. Here 1 by 4 pi epsilon 0 and Q by R square is a constant. We can take it outside. So equation phi is equal to 1 by 4 pi epsilon 0 Q divided by R square integral of ds. Integral of ds is the total surface area of this sphere. So this is equal to 1 by 4 pi epsilon 0 Q divided by R square integral of ds, that is the surface area of the sphere, is 4 pi R square, where 4 pi cancels. R square cancels. So the remaining term is phi is equal to Q by epsilon 0. So this is Gauss theorem. Phi is equal to Q divided by epsilon 0. The electric flux is 1 by epsilon 0 times the net charge enclosed by the surface. Thus we proved Gauss theorem. Gaussian surface. Gaussian surface is a hypothetical surface which encloses a charge. We choose Gaussian surface in order to evaluate the surface integral of the electric field produced by the charge enclosed within it, and hence to find the electric flux. A clever choosing of the Gaussian surface will make the problem easy to find the electric field of many symmetrical charge distribution, otherwise which is very difficult to find the electric field by the direct application of Coulomb's law and the principle of superposition. use Coulomb's law from Gauss theorem. So in order to find Coulomb's law from Gauss theorem, I am considering a positive point charge. I am also considering a Gaussian surface which is in spherical shape, which is a spherical surface with radius r. Due to symmetry, both the area element as well as the electric field will be in the same direction. So angle between ds and E can be written as 0 degree. Theta is equal to 0 degree. According to the equation of flux, flux phi is equal to integral over E dot ds or integral over E ds cos theta. Since theta is 0 degree, cos 0 is 1. So this equation becomes phi is equal to integral E ds. Or I can write phi is equal to E integral over ds, where integral of ds is nothing but the surface area of the Gaussian surface, where the Gaussian surface is spherical in shape. So integral ds can be replaced as 4 pi r square. So here I got an equation for phi. Let that equation be number 1. Now I am applying Gauss theorem. According to Gauss theorem, phi is equal to q divided by epsilon 0. Let this equation be number 2. Now we will equate 1 and 2 where both LHS are same. So E into 4 pi r square is equal to q divided by epsilon 0, or E is equal to q divided by 4 pi r square epsilon 0, where we got an equation for electric field. Suppose I am placing a test charge Q0 on the surface of the Gaussian surface. Definitely Q0 will experience a force due to the plus Q which is in the center of the Gaussian surface. And that force F is equal to E into Q0. Instead of E, we can substitute Q divided by 4 pi r square epsilon 0. So the equation becomes 1 by 4 pi epsilon 0 Q into Q0 divided by r square. This equation is Coulomb's law. The Coulomb's law, force is equal to 1 by 4 pi epsilon 0, the product of the charges divided by square of the distance between them. Hence, we deduce Coulomb's law using Gauss theorem. So here is the first application of Gauss law. This year you have to study only 2 applications, where one application is electric field due to an infinitely long straight wire, and the second application is electric field due to a uniformly charged plane sheet. The third application is excluded from your syllabus for this academic year 2020-21. So in order to find the electric field due to an infinitely long straight wire, here I am considering an infinitely long straight wire where there is a Gaussian surface which is in cylindrical shape. R is the radius of the Gaussian surface. L is the length of the Gaussian surface. In the case of the cylinder, it has 3 surfaces, 2 circular surfaces and 1 curved surface, where S1 and S3 is the circular surface. Angle between DS1 and E is 90 degree. Similarly, angle between DS3 and E is 90 degree. In the case of the curved surface, both the area element and electric field are in the same direction due to symmetry. So angle between DS2 and E is 0 degree. Now if lambda is a uniform charge density, then charge enclosed by the Gaussian surface Q is equal to lambda L, where L is the length of the Gaussian surface. According to the equation of electric flux phi, phi is equal to closed integral of E dot ds. I can write this equation as integral of S1 E dot ds plus integral of S2 E dot ds plus integral of S3 E dot ds. Now I am expanding E dot ds, where E dot ds is E ds cos theta. This is equal to integral over S1 E ds cos 90. In the case of the first surface, angle between DS1 and E is 90 degree. So instead of theta, I can write it as 90 degree plus integral over S2 E ds cos 0, where S2 is a curved surface. So the angle between DS2 and E is 0. And the last one is integral over EDS cos 90. Again, S3 is the circular surface where angle between DS and E is 90 degree. Cos 90 is 0. So the first term and the last term becomes 0. So the remaining equation is flux is equal to integral over S1 EDS where cos 0, S2 EDS where cos 0 is 1. So flux is equal to integral over EDS, or I can write flux is equal to, instead of integral ds, it is nothing but the curved surface area of the cylinder. So phi is equal to E into 2 pi RL, where 2 pi RL is the curved surface area of the cylinder. Here we got an equation for flux. E is equal to 2 pi RL. Let this equation be number 1. Now I am going to apply the Gauss theorem. According to Gauss theorem, flux is equal to Q divided by epsilon 0. Let this equation be number 2. Equating these equations, equating 1 and 2, we can write E into 2 pi RL is equal to Q divided by epsilon 0, or E is equal to Q by epsilon 0 into 2 pi RL. Instead of Q, I can write it as lambda L. So E is equal to lambda L divided by epsilon 0 into 2 pi RL, where L is common, it cancels. So E is equal to 1 by 2 pi epsilon 0 lambda by R. This is the equation for electric field due to an infinitely long straight conductor where E is inversely proportional to the distance R. So this is how you derive an expression for electric field due to an infinitely long straight charged wire using Gauss theorem. Electric field due to an infinitely charged plane sheet. So here we consider an infinitely charged plane sheet of surface charge density sigma, and charge Q is equal to sigma into A, where A is the area of the plane sheet. We wish to calculate the electric field at the point P. In order to apply the Gauss theorem, here we are considering a Gaussian surface which is cylindrical in shape. Here, due to symmetry, the E is always normally outwards in the direction. Through the curved surface, since the feed lines are parallel to the curved surface, the flux will be 0. So flux will be through this circular surface of the cylinder. The electric field at the point P and P dash must be equal in magnitude and in opposite direction because P and P dash are equidistant from the plane sheet. According to the equation of flux, phi is equal to integral EDS. I can write this as E integral ds, where integral ds can be replaced as the area of the plane sheet. So phi is equal to E into area. This is a flux through S1, that is one surface. Similarly, the flux will be through S2 also. So the total flux phi will be equal to EA plus EA. Flux through both the surfaces are equal because electric field due to the both surfaces are equal. So total flux phi is equal to 2EA, where this equation is number 1. We will apply Gauss theorem. That is, flux is equal to Q divided by epsilon 0. Let this equation be number 2. Equating 1 and 2, 2EA is equal to Q by epsilon 0, or E is equal to Q divided by 2A epsilon 0, where Q can be replaced as sigma A. So the equation becomes E is equal to sigma A divided by 2A epsilon 0, where A cancels, and the final equation E is equal to sigma divided by 2 epsilon 0. This is the electric field due to an infinitely charged plane sheet, where electric field depends only on the surface charge density and permittivity of the medium. Clearly, E is independent of the distance R. So, if charge Q is greater than 0, that means if charge is positive, the direction of electric field is radially outward the surface. If charge is less than 0, that means if Q is less than 0, if Q is negative, the electric field will be radially into the sheet. So this is the equation for electric field due to an infinitely charged plane sheet. So that's all for today. Thank you for watching me.